All right. So a warm welcome from my side. I am very pleased to have Alexander and Birgit with me again today for part 2 of the 3-part webinar. Before we start, I would like to give you a quick tour of how the event will be managed. So you are currently muted. But obviously, we invite you to use the Q&A box at the bottom of your screen to post your questions during the webinar, and we will make time at the end to answer them. If by any chance we don't have time to answer all the questions, depending on how many questions are coming, then please feel free to post your questions using your name, and we will get back to you after the live session. So we apologize if we cannot answer all the questions during the live session. Sometimes we are a bit restricted by time, and we would like to respect everybody's schedule. Thank you. Right, so today I'm going to dive right into it by presenting our speakers. I will start with Birgit, my colleague at PreciPoint. And Birgit is head of business development. She's been on many webinars with me in the last month, so I don't think I need to introduce Birgit in much details, but a warm welcome, Birgit. Thank you for being here again. And
thank you, Alphonse.
You're welcome. And I would like to introduce Alex Stickler-Bareng, who is International Sales and Business Development Manager at Tissue Agnostics. And you will get to hear Alexander right now as he talks us through nuclei segmentation using AI software. I'm really looking forward to it. And with this, I quickly introduce today's agenda, and will now pass on to Alexander to start his presentation.
All right, thank you for having me. So let's get into it. I'm going to share my screen. Give me 1 second, please. Okay, so I hope you see it. Yes, okay.
Thanks.
Good. All right, so we are going to talk about deep learning today. And so I'm going to go over briefly what we did last time, and then branch off into deep learning. And I'm going to give you some practical examples of how how Tissue Agnostics uses deep learning for nuclei segmentation, and how we then combine that with what we did in our last session, how we utilize machine learning for tissue classification, and how the combination of these two very powerful tools can create a wealth of information very, very quickly without the need to know too much about image analysis, except the way a user interface works, which can be easily learned. So we started off last time with a definition of artificial intelligence, and we were primarily focused on machine learning. So artificial intelligence is basically a wide-ranging branch of computer science concerned with building smart machines capable of mimicking problem solving and decision making of the human mind. And so this is a little infographic for where machine learning and deep learning are placed within that realm. And deep learning is a subset of machine learning, and this is a different way of extracting information from annotated data and raw data. And so what we're going to go into that now. So this is a slide I showed last time. The main part here is that I'd like to focus on is deep learning models and what automatic feature extraction means. So here, just to go over this quickly again, we have 4 different types of applications that we can utilize: classification, classifying types of images; detection, is there a parathyroid gland? Is there an object of interest within this image? And then a bounding box having been generated around those images, around those objects of interest. And then we have 2 different types of segmentation. So semantic segmentation is detecting all objects of one type, and instance segmentation is is detecting each and every one of those instances and with bounding boxes, and within those bounding boxes, then segmenting those objects of interest around the borders of those objects. A typical workflow is can look like this. So you have raw data and you pre-process that, and then you can utilize one of those machine learning based methods. In this case, we'll be using deep learning approaches, and then you can go through a post-processing and evaluation phase. What this looks like practically for the algorithm on the other side basically is you have an input image. In this case, we're looking at an H&E stained liver biopsy. And the classification task was to identify if this tissue is healthy or diseased. And in order to do that, to make that decision, bounding boxes were placed around objects of interest, and then semantic and instance segmentation were used to identify each of these objects of interest. In this case, they were nuclei here. So, and a deep neural network. So for deep learning applications, we typically use deep neural networks, and this is what it kind of looks like. It can vary from network to network. There can be they can be much more complex than this, or a little bit simpler. The primary function of this deep neural network is to automatically perform feature extraction from the given data, and then create a model for detecting objects of a certain type. And because these are so complex, you can the features that are automatically extracted from an image can sometimes be unpredictable, and you don't know what an algorithm, what a deep neural network or an artificial neural network will what features it thinks make an image or make an object of interest special and detectable. So these nodes here, these circles are called nodes or neurons in an artificial neural network, and they're filters. You can see it as a multi-level filter, and each individual one can contain a mathematical property or a function that multiplies or adds, and then the next layer can do the same thing in a different way, for example. And it filters this information in a variety of ways. But the main thing that the main purpose of this is to give it raw data on one side and annotated or classified images on the other side. So you're giving it the front and back end to an equation. And the neural network in the middle is what figures out, it figures out what that variable is. And then in the end, after you've gone through a training phase, a model has been created that's within these three levels of nodes or layers here. And in the end, the goal is then to remove the annotated images, the output layer, and let it do it on its own with a new set of images. So that's basically what the difference is between machine learning and deep learning. Machine learning requires you to give it input every time you start a new training model, and this one, you give it raw data and the input, and you let the feature extraction happen on its own. That's the main purpose of a deep neural network. And so what this means for us, for TissueGnostics and for StrataQuest, is we get images like these, and these are tightly packed, densely packed nuclei in an immune organ, and these are very, very difficult to segment. When we create a model for a deep neural network, the information we give it is of vital importance. And so the type of tissue of the tissue environment, the immune organs or lymphoid structures, is what our deep neural network was made to specialize in. So the nuclei in this image are very densely packed and are very low in intensity, which makes them almost impossible to somewhat accurately detect using classical image analysis methods. And when creating a DNN, we must accurately and manually annotate each and every one of these nuclei in multiple images, just like this one, before introducing it into a neural network. So the quality of the annotations you give a neural network will define the accuracy of that neural network in the end. So you have to be very, very particular with the training data. Yeah, so that I hope that is a kind of a low-level introduction to deep neural networks. My colleagues have trained me a little bit on this, and that's kind of what I gather. We can go down a rabbit hole of technical descriptions and so on, but I'm probably not the best person to talk about that. My colleagues here are way more knowledgeable at this stuff than I am. But I can show you what this looks like practically now in images. I'm going to share another screen now. And we're going to look at this sample in particular first. Show all windows. Sorry, 1 second. This one. Okay, so I hope you see a different screen now. Okay. And you probably see nothing here. This is the raw data. This is what we have from the scanner. And unfortunately, it's very difficult to see anything here. This is the raw DAPI channel of a lymphoid structure, a lymph node, I think, or an immune organ. And this is the main interface of StrataQuest. We have an algorithm here. And the reason why we call the software StrataQuest is because an analysis pipeline can be built in multiple layers. One layer starting off simply and then moving more and more complex, building on top of each layer. And we would usually start with maybe a tissue detection or a nuclei segmentation, and then start building an algorithm based on that, to find multicellular structures or relationships between single cell populations, or single cells and multicellular structures, and so on. But for now, we're going to focus just on the nuclear segmentation. And we have two different ways of doing that. A classical nuclear segmentation algorithm, it's been around since the inception of tissue gnostics, which was 2003. It's a very robust algorithm, but it can't really handle nuclei that are this densely packed. This is, I think, difficult, if not impossible, for most classical image analysis methods of nuclear segmentation. And I can demonstrate that to you. What you're seeing here is an enhanced view of these nuclei. So they've been boosted. The signal has been boosted, but it's very, very low in intensity, which is why we had to boost the image so you can see something. The classical nuclei segmentation algorithm looks like this. So we have a detection level here in every one of these StrataQuest layers, and every StrataQuest layer you have a pre-processing phase, a detection phase, post-processing, manual correction, and two different measurements options here. And in the detection phase, there's one detection phase per layer. And here we've got an algorithm where you can select an input image that's usually a DAPI or a color-separated hematoxylin layer in bright field. And then we have a nuclei size. And this is a slider, and it goes all the way up to 200 because images can range from 10x to 100x, and the magnification defines what you set this parameter at. So if you're using a 100x magnification image, then you would have to set this closer to 80 or something, or 200. And I think this is a 20x image, and so our slider is at the bottom end here, and these nuclei are quite small. We have some post-processing options here for removing objects by their area or by their staining intensity. And we also have an automatic background threshold. And this is vital for distinguishing objects from background, objects or non-objects. And what we're asking the system to do is define a lower and an upper threshold. And within this range, we can look for objects, or we can look for a cutoff between the background and the foreground being the nuclei. And we do this by a linear scale. I can't, why this, hold on. Let's see if I can put this here. Do you still see my screen? Yeah, okay, good. So there's a tool here that allows me to see the staining intensity of any given pixel that I choose. So if I go here and select some background area like this here.
Sorry, Alex, we
yes?
do see a screen, but I'm not sure if this is the screen you want us to see.
Oh.
We do see like a pull down menu with a pre-processing. Okay, now we can see your mouse again.
Ah, okay.
Yes, that's right.
Good. Okay, it's right. the oh, I can move this. All right, sorry. It's the zoom thing that comes in the top, which blocks my my toolbar at the top. So, okay. So if I click anywhere on here, I get this a readout of the gray level, and we're using a linear scale here. This is a monochrome image. Even bright field images can be color separated into monochrome images, and because this is a linear scale, we can use this to set a threshold on intensities, and therefore we can separate foreground from background. So these very dark areas have a very low gray level value, and these brighter areas have a higher one, a 46. And we're using, this is an 8-bit image, so the scale goes up to 255. So you can see how low in intensity this really is if the top end is at 40. And so this tool is what we'll use to set a give the system an idea of where the background threshold is. And so there's a little preview button here that I can use, which will allow me to make some changes in real time and see how this changes the detection. And so if I, let's say, increase the nuclei size here to 9, we will get under segmentation. There are multiple nuclei here that are bunched together in these detected areas, which is under segmentation. And if I go too low, we'll get over segmentation. So this is an algorithm that you can fine tune, and you have a lot of control over this. And this algorithm works really nicely for most applications. But if we're talking about immune organs where tissue is very, very densely packed, it's almost impossible to get an accurate detection using the classical nuclei segmentation method here. So comparing this now with the DNN, we get a very different result. And this is this is what our DNN is able to generate on a very, very difficult image where a lot of nuclei are too dim to even detect or out of focus. And you can see how nicely some of these, most of these nuclei are detected by a contour that really wraps around each one. And the reason for that is because the algorithm that we're using, so the deep learning model, was trained on images just like these, as well as others. So it wasn't only, I think, trained on this one, it was trained on a multitude of organs, and is therefore quite flexible. So if we compare that with the classical nuclei segmentation, you can see how it does work in some cases, but in others where intensities are a little bit different, you can see how clunky it starts to look. And the classical nuclei segmentation works really well for other organs where there's a little more separation between nuclei. It works very well in tissue, but for applications like these, the deep learning neural network works very, very well. And the best part about it is that there are no parameters to set. It's a model, and it's a pre-trained, pre-made model. You just apply. There are no parameters to tweak. There's nothing to learn about this. You just select it. And there's one model we have right now. Here we're testing others at the moment, which will also be very interesting in the future. And that's the basic model here. And now I'm going to show you what this looks like on other samples. So let's try a new share. I'm going to share a different project. And I'm going to share the one we worked on last time. So this is if you joined last time, you'll probably recognize this one. This is a breast cancer needle biopsy. I hope, yeah, it's the pink one. Yes, you see the pink one, yeah. Okay, good. So it's a breast cancer needle biopsy in which we did a very nice classification. It looks like this. And I utilized the classifier here to create 5 different tissue classes. We have background in gray. We have the tumor areas in red. So if I flip back and forth between the original and this one, we can see these tumor areas here. We have areas of high accumulations of immune cells in green, and we have fat cells here in yellow, and we have the interstitium in purple or magenta. And this was the classifier, but we can very easily combine this now with the deep learning neural network for nuclei segmentation. Where did I put that? Here, nuclei segmentation, DNN. Got this algorithm here. I select the input image, which is actually a color separated hematoxylin. So of course, it's this hematoxylin and eosin. There's a blue marker and a pink marker, and that's what gives us these 2 different colors here. And by color separating these, I can then take a look at, let's see, the gray image of the hematoxylin versus the eosin. And this is what we'll use for the DNN. The DNN will then utilize the hematoxylin color separated image, and we can combine that now with the tissue classification based on machine learning, and now we get this really nice segmentation of our nuclei, and you can see them now encircled in a black line, and they're color filled with black or gray. And when we have these nuclei, we're also able to measure them, and we can find out how many there are per tissue class. So if I want to see the let's say the immune cells, let's say the immune cells here, there's a very nifty tool called the backward connection. So I can put all these nuclei. Each of these bars here are actually dots that are categorized by their location in the tissue. And by right-clicking on this, I can view the backward data for this gate, which will show me all the immune cells that are all the nuclei that are found in the category immune cells that we used the tissue classifier to segment those classes in. So if I zoom in, you can see all of these immune cells here, and I can do the same thing for the tumor. And the great part of this algorithm, of this nuclear segmentation algorithm based on deep learning, is how flexible it is. You can see there's a huge difference in size between these tumor cells and the immune cells. So if I flip back and forth here between these various different types of nuclei, so in red you can see the tumor cells, and in green you can see the immune cells. There's a huge difference in area between these, and that's because the algorithm, the model that we created, is so flexible. It's you can use one algorithm to find both types of cells, even though they're so different in area. So I have one more example to show you, which is really cool, and I hope I'm not going over time. Just do a new share really quickly. Okay, so this is an immune organ, and I'm not sure exactly what it is. I think it's a lymph node or something. And here we're doing basically the same thing. And I've put in I've used the classifier and the DNN, the deep neural network for nuclear segmentation, and I've combined the 2 here. And I've got more classes than I thought I would use, and I got 9 classes here. So I've got the background in black, germinal centers. We have the mantle zones. Those are these blue areas here around these germinal centers. We have T cell zones in between these very bright objects here. And we've got epithelium in green. Then we have mucus areas here. We're not sure exactly if these are mucus areas, but we classified them as something here just so we could detect them. On the bottom, we have muscle. And between the muscle and everything else, we have the stroma. And then we also have endothelial blood vessel borders here. And those are 9 classes, which is the most I've ever used in a classifier. And we got some pretty cool results. Where is that classifier? Here we go. So if I zoom out, you can really see this this type of segmentation. And there's probably a little bit that can be improved here, but it was I think it's pretty good for a quick classification. And flipping back and forth here, you can really see the classifier doing a good job there. You even got the muscle, the endothelial areas here detected. You have those germinal centers in red. You have T cell areas in yellow. You have the mantle zones in blue, and endothelium in green, mucus areas in yellow. So this is a lot of information. And you can now combine this with the nuclei segmentation. So if I go to here, so this is actually the classical nuclei segmentation, DAPI nuclei. Here we go. So if I zoom in, you can see how densely packed these nuclei are. And although we can't catch all of them, this is vastly more than you would ever be able to detect using a classical nuclei segmentation algorithm. And if I show you that here, you can see what it would look like with classical nuclei segmentation. We're missing entire swaths here. We're getting over segmentation. It kind of looks really messy. But if you flip back, this is much cleaner. And on top of all of this, you get a this is a tool. This is one of the great parts about StrataQuest. You can perform an in-depth single cell analysis. And when we double click on these nuclei, you can see them measured in scattergrams here. And we can see entire cell populations based on where they are in the tissue and what markers they're positive on. So if I double click on any one of these nuclei, let's see the cellular mask on this particular nucleus, you can see it's located in the germinal center. And then when we measure them on each of these channels, so we've got Alexaflor 594, rhodamine, FAM, I don't know which one this is, and the DAPI. We also have, I think, the Psi5, yes. And so we've got scattergrams that will measure the staining intensity of each of these channels. And so you can find double and triple positive cells and where they are in the tissue, which tissue class they belong to. And these scattergrams are really nifty tools where you can find, you can use heat maps to find the highest concentration of highest concentrations of where these cells are in, and also, of course, they're all color coded depending on what class they belong to. So unfortunately, I don't have too much time here to go into all this, but it is a wealth of information you can generate using a very simple algorithm in StrataQuest. And all of that is made possible by advances in machine learning and deep learning. Luckily, we've got experience in this since 2003. So all the classical image analysis and experience that we've gathered over the years was just enhanced by the advances in AI. So looking at all of this, maybe from a one of these perspectives might be interesting. So let's take a look at the mantle zones or germinal centers. Maybe those are really interesting. Backward data for germinal centers will show us the nuclei there. Germinal centers, should be the backward data. Well, it needs to be in here. Yeah, so you can't really see it, but they're highlighted in red. If we really zoom in, you'll be able to see them highlighted in red, and all the other cells are in green. So it's just a matter of displaying it properly and color coding things, because when we're dealing with so many different classes, you start to run out of colors. And yeah, so deciding which colors to use becomes really, really important. But the deep learning nuclear segmentation is a really powerful tool that allows you to just see so much more once you combine it with the machine learning tissue classifier. So I think I'm out of time at this point.
All right. Yeah. I mean, thank you very much, Alex. I know you are very excited about that stuff. So, I can see. No, this is wonderful. Thank you so much. We do actually have questions. So what I would like to do is invite the listeners who have actually posted questions to stay with us for 5 more minutes. So we can try and answer most of them, if that's a suitable proposal.
And of course, also all the others that are happy to join it for a little bit longer, right?
Of course, no, of course, yeah. But if you have some other appointments at the back of this, okay. So let's pick a first question.
Yes, it's actually super difficult. I think I will just start pretty much from the top. Thanks already for all the positive comments. Thank you for that. I take one question from here, that is, what is the deep learning model you use for the nuclear segmentation? You know, Alex?
The deep learning model was created in-house. So that was created by one of my colleagues who's been working at the Medical University of Vienna for I don't know how long, but he's the one developing these algorithms, and he spends a ton of time annotating things. And yeah, so we're working on multiple new I think we are, because that's what I heard today, new models potentially. The one we have now is very robust already, and it's only going to get better from here on out, I think. So the deep learning model was created, as I said, on these to be flexible enough to deal with very, very difficult and densely packed nuclei from tissue like immune organs. And yeah, that.
Then another question. Do these deep learning modules and multifocal segmentations also work for confocal? And I think there was another question that I'm combining just as well for fluorescence.
Oh yeah, so they work in both bright field and fluorescence images, regardless of where they come from, I guess. They even work on imaging mass cytometry images. So if you're using a mass cytometer, they work on those as well, as long as you have images that show nuclei in at least 20x or 10x, it'll work. Especially confocal images. Yeah, that's yes.
Awesome. Alex, what do you think is the future of tissue segmentation and classification?
Oh,
an easy question, right? Can you answer quickly?
I have no clue. That's the future. I think these tools will become easier and easier to use. I mean, they have already in the past years. The tissue classification has existed for I know at least for 5 years already, but it hasn't been this easy to use ever. And combining these two tools have never been so easy to use, I think. So I think in the future it'll get easier and easier to obtain information like this and to ask more and more complex questions, because tools become more accessible and easy to use over time.
Then there was a question on whether it's based on UNet architecture. And I think, yes, that was the voice from the tissue gnostics off that has said it's based on a UNet classifier. So I can answer this question already.
Thank you.
Then one more question maybe. What kind of formats can you actually handle?
We can handle formats from most scanning systems on the market. So if you're familiar with scanners, they all have their own type of image format. I think there are groups of there's a group of people working on a unified scanning format, the open microscopy environment, but we can use those as well. We can use generic file formats, TIFFs, PNGs. the PreciPoint file format, of course, Zeiss, Olympus, Nikon, any kind of scanner you can imagine. We probably have a translator basically or an importer for those files. So yeah, we're pretty flexible when it comes to image type.
One last question, maybe.
Yeah.
Is it possible to segment neurites?
Neurites, yes. I mean, you could maybe use the classifier for that, but we have specialized algorithms that can identify neurites and dendrites, neurons, as well. So I've developed apps for neuroscientists that wanted to classify dendrites. The problem with that, though, is that it's a 3D structure, and you have overlapping structures. And if you're looking for an axon, and there's an overlapping dendrite or a tertiary dendrite, it's very difficult for an algorithm to segment 3D structures in 2D. So there is some level of manual annotations you have to do to those images in order for the software to quantify that. But yeah, definitely, we have specialized algorithms for that. They're really cool. We have apps on our website you can take a look at. If you go to the App Center, tissuegnostics.com, there's a huge collection of apps. There's a library of apps that's growing constantly, and you can check those out.
Okay, how are we doing there for questions, Birgit?
There's more questions coming,
yes.
and
yes, I know.
Very hard to take it down. Let's take one last question, and then I hope for everybody that we could answer a lot. And as again said, please reach out to us, so we will note them down and get back to you, and try to answer them afterwards, right? So that we don't take too much of your evenings or afternoons away. The last question was, Alex, do you know whether you can also do segmentation on white matter hyperintensities?
I honestly have no clue what that even means.
I didn't know.
I'm not a neuroscientist. I really specialize in utilizing this software, but I think it's a matter of showing us the images and going over them together. So we on a regular basis create analysis algorithms from scratch, custom analysis algorithms for very specific research purposes and or research questions. So if you have images, you can send them to us or get in touch with me, and you can upload your images to us, and we can discuss how and what structures you're interested in automatically identifying. If you can describe them and the characteristics of those images and what differentiate them from other structures in the images, we can basically teach our software to do that as well. Similar to the way you would treat a machine learning tissue classifier, it's kind of the way we deal with algorithms on and coding here. And so there's a lot of flexibility in this pipeline, and a lot more that I haven't even touched on. I basically went through the AI only in this software. There's a lot of classical image analysis that we can utilize for detecting structures of any kind. It really comes down to if you're able to differentiate them yourself with actual differentiating structures in an image. So I would get in touch with us, send us some images, please, and we'll see what we can do. Usually we can detect something in any kind of image. I think that would be a good way forward.
Very good, very good. Birgit, I think
I just wanted to summarize that I think generally in all these problems, be it scanning or analyses, there's so many different applications each of you have. Sometimes we haven't come across them yet, right? But that doesn't mean that it doesn't work. So feel free to just reach out to us. We're always happy to both do scan trials as well as trials on a scan to do the analysis, right? So reach out to us. We'll be happy to see how we can help.
Definitely.
That's right. Thank you very much. Right. So next event is already on Thursday, this coming Thursday at the same time. We'll look at TMA cause. So again with Alex. So if you haven't registered yet, you may do so by going to precipoint.com/en/webinars, and we would be very happy to see you again on Thursday for the third and last part of the series. Right, reach out to us, please, if we haven't unfortunately answered your question because of time, and we actually did not want to go over time, but we actually did. So thank you for your patience. So here are the email addresses of our speakers today. Please feel free to reach out. And that would be it from our side for today. One last thing before as you leave the Zoom session, you will be directed to a quick survey, which is anonymous, and we would really appreciate if you could take half a minute to answer the questions, so to help us get better at what we're doing and get at our webinars. So that's it from our side. Thank you so much. It was a very lively discussion.
Yeah. Thank you for the questions. Yeah, that was good.
Thank you, everybody, and see you soon.
All right. See you on Thursday.
Thank you. Bye-bye.
Bye-bye.